Okay, we are rocking and rolling in the wonderful world of structural analysis. We are still in shear and moment diagram territory, and we're kind of going to be there for a little while, so just be ready for that. Homework 5.1 is currently being graded. That solution should be up. I had to check right before here to see if the lecture notes were up, and I forgot to post those, but these lecture notes are now posted. I'll make sure homework 5.1 solution is posted today. Okay, 5.2 is due, and 5.3 is assigned today. It's going to be kind of like that for a little while. I'm going to shut this. Come on. All right. One thing that's worth mentioning is that on Wednesday, if you have a laptop, it would be a good idea to bring it because it's not desperately necessary, but it's really good to have one in class because what we're going to do so what we're going to do today is we're going to handle shear and moment diagrams subjected to distributed loads. And then on Wednesday, we're going to handle what about shear and moment diagrams subjected to triangular loads. So today's going to be uniformly distributed, and then Wednesday's going to be triangular. And in order to draw a shear and moment diagram for a beam subjected to a triangular load, there's really like only one way of getting it right, and that's cutting a section and writing equations. And I want to use Excel to back up what we do. And so your homework assignment that I'm assigning Wednesday and that's due Friday is actually just that. You're actually going to build a little Excel sheet that will plot the shear and moment diagram of a beam subjected to a uniformly distributed load, but you're doing it in Excel. And Excel is, already one of the software packages that we use in here. We're actually going to use some what I would call real deal structural analysis software a little bit later in the semester. I've traditionally taught RISA 2D. I've been toying around with switching that to another package called Mastan. There are some advantages that Mastan has. For one, and I can already hear the groans, so you stop in advance. But one of the advantages of Mastan is that because it is MATLAB based, no groans, we're not using MATLAB or anything, but because it was written in MATLAB, it's Apple and Windows friendly, so it'll work on either operating system, and it's free. And it's actually a pretty robust software package. One of the downsides is that there are some limitations to Mastan, like it can't do triangular loads, but I think in the grand scope that might not be the biggest deal in the world, but I'll make my decision a little later. We've got plenty of time on that. Okay, any questions? All right, so today we're going to continue, I hit the button. Today we're going to continue our discussion of shear and moment diagrams, and we're going to continue the use of our relationship between loads and shears and moments. So the idea is that when you draw a shear diagram, you are essentially integrating the load diagram. It's very visual when you do it, but it's kind of the idea. And when you get a shear diagram, you then integrate that shear diagram to obtain the moment diagram. And we made a series of conclusions about the math that made our life a little easier and made what we did when we constructed the shear and moment diagrams far more intuitive than if we just cut a bunch of sections and listed them in a table and plotted them on an X and Y coordinate system. I think that made it a lot more straightforward. And hopefully the lecture last time was it really tied a lot of those concepts together. We took a really simple beam, but we really did that beam. I mean, we drew the shear diagram, we drew the moment diagram, we tied that example back to what we had did before where we cut a section, and we looked at different ways you could get those forces. And so hopefully that you get the idea. And so if you get the idea, all we're going to be doing for the next few lectures is taking that idea and just adding some stuff to it. And so the first thing I want to add to it is a distributed load. Now, a distributed load goes one level up on that scale of mathematical functions that we introduced at the beginning when we first started talking about shear and moment diagrams, right? Remember I said when you're when you're first starting to learn how to draw shear and moment diagrams, that one of the patterns that's worth recognizing is the relationship between the derivatives and integrals of polynomials, right? So if you have a constant, you take an integral of that, you get a linear function, you take an integral of that, quadratic, et cetera, et cetera, et cetera. What we did last time, we had regions of no load. So our shear diagram was a bunch of constant functions, and our moment diagram was a bunch of linear functions. Well, we're going to take it one level higher. So whenever we're dealing with distributed loads, in this case looking at uniformly distributed loads, our load is constant, okay? So if you integrate a constant function, you get a linear function. So the shear diagram, instead of being a bunch of stair-step regions when you're dealing with distributed loads, you're going to have a bunch of lines, okay? Now you can make some very similar conclusions about that shear diagram. For instance, here's a load, here's the shear diagram. What is the slope of that line? It's the load, right? Or negative load. Why is it negative? Because the load's going down, this is going down, okay? Now, if this is linear, I integrate that. What is the integral of a line? It is a parabola, a quadratic function, right? So whenever you have a linear shear diagram, you should have a quadratic moment diagram. Now, how you construct that, this is my little mnemonic that I use. I use the phrase either a lot to a little or a little to a lot. So let me explain what that means. Let's go back to graphing. This is a line with a lot of slope. This is a line with a little slope, right? With me so far? So the idea is that here we have, let me use my little pen here. Here, this is a lot of shear. And so a lot of shear means, I'll say lot of slope. Here we have, let me erase my quotation marks over here because it's not kind of shear, it is shear. Here we have a little shear. So here we have little slope. So the idea is whenever we're drawing the moment diagram, we have to ask ourselves if the moment diagram is going to go like this, which I call a lot to a little, or if it's going to go like this. A little to a lot. I will use that phrase a lot just because I think it's simple, it's easy to understand. But understanding that pattern of moment diagram, looking at the shear diagram and recognizing what's going on will make your life a lot easier. What we're going to do is spend the rest of class discussing a particular beam example. But before we do, I have a geometry problem I want to illustrate with you because so today we're doing uniformly distributed loads. Next lecture we're doing triangular loads. With both of those problems, there is a particular challenge in geometry that I kind of want to do off to the side. I want to handle that before we start going into the shear and moment diagram because I don't want to be drawing the shear and moment diagram and then, oh wait, we got a geometry problem to solve. And these are very simple, but I think it's valuable to go ahead and do this first. And I'm going to pull up the notebook here in a second. So here's a geometry problem I want to show you. So this is a sort of snippet of a shear diagram. And as you know, what we are going to have to do is determine the areas of the shear diagram. Okay? So I have a shear diagram that jumps up 25 kips and then it crosses down to negative 75 kips. And it does this over a distance of 25 feet. Okay? So the question is, how do we determine the area of these two triangles? And specifically, how do we do it easily? Okay? Now, let's recall, before we break this out, let's recall that the slope of this line will be something that we always know, because the slope of that line is going to be equal to whatever the magnitude of load is across this region. Now, can anybody look at this line and tell me what the slope is? Say it again. -4. That's exactly right, because your change in y is 100, your change in x is 25, and so the slope is -4. Is everybody with me so far on that? So let me pull this up in the notebook just so everybody has this. No, I don't want to keep my ink annotations. Okay, so just so we're clear, hold on. The slope is -4, and if we want to be super consistent with our unit system, it is 4 kips per foot. Okay, and how did I determine that slope? It is the change in y over the change in x, which is -100 over 25 feet. Is everybody okay with that? Now that calculation we typically don't have to do when we're drawing shear diagrams because we know what the slope is from the load. All right? Now help me out. How do we determine the area of a triangle? 1/2 base times height. So if we look at each of these triangles, we know what the heights are. This is 25, this is 75. What about this? We need to know the base. Okay? A very easy way of determining the base is to use the relationship above, right? The slope is the change in y over the change in x. I want the change in x. All I have to do is flip. So the change in x equals the change in y over the slope. I propose that this distance here, which we'll call x1, we'll call this distance here x2. x1 is just the change in y over the slope, which is 25 kips over 4 kips per foot. And we don't need to worry about the negatives, and you're going to see why here in a bit. Because we'll take the negatives, we'll take that into account when we look at the internal area. So what's 25 divided by 4? Yes?
Why is it 25 down there but -100 on top?
That's a great question. Because what I was, when I was determining the slope, in order to determine the slope of this line, I wanted to know, okay, the entire length is 25. What's the entire change in y? From 25 to -75. That's 100. That's a fair question. Keep in mind, though, we're not going to have to do that when we draw shear diagrams because we're going to know what that slope is. All right. What's 25 over 4? 6.25. And so what's x2 going to be? Let's see if you can follow that along. 18.75. Do I have a second on that? So there you go. So I propose x1 is 6.25 feet, and I propose that x2 is 18.75 feet. What happens when you add those two values together? What do you get? 25, right? So that makes sense. And also just look at the scale, look at the numbers. Does intuition tell you that the values make sense? Yeah, right? So if I want to determine the area of this first region, we'll call this region 1. We'll call this region 2. All I have to do is say A1 is 1/2 25 kips times 6.25 feet. And area 2 is 1/2 -75 kips times 18.75 feet. I don't want this part to be a challenge on the next problem. Does that make sense? That's the idea. All right, so what do we get for A1 and A2? try A1 first. Ow. 78 and an eighth, you said? So we'll say like 78.125, and what about the next one? It'll be negative. Say it again. All right, do I have seconds on these? Okay, now, what are the units? What should the units be? No. The height is kips, because we've already taken that into account. Right? Foot kips. This is a shear diagram that we are integrating. The integral of the shear diagram is the moment diagram, so the units better be foot kips, right? All right, does that make sense, that concept? I don't want this to be a challenge later, okay? This should be the stuff that we need to make sure that we're comfortable with, because when we do our next example, I want that to be straightforward. Sound good? All right. Do I need to leave this up here? Okay. So if you're okay with that, instead of going back to the slideshow and then going back to this, let's just do this. Here's the problem that we're going to do. I want to draw the shear and moment diagram for this beam. Now already this beam is ratcheting it up just a tad from the last problem that we did in class, okay? For one, we've got the distributed load. That's kind of the whole point of today's lecture, is handling that distributed load, okay? We also have point loads together, okay? And third, while this doesn't really matter, and you've already dealt with this on your homework assignment, we got an overhanging beam. It's not just simply supported, okay? So there's a lot going on here, but I promise you this is no different. This is no different. The concept is just the same. Now, while you're copying this down, and I'll give you a minute to do that, one of the things that I did not give you are the reactions. I did not give you the support reactions on this problem, because sometimes I'm going to give them to you, and sometimes I think it's valuable to go through the exercise from start to finish. I want you to see where the reactions are coming from, and I want you to see how the reactions obey the principles of equilibrium, not just from the equations, but when you're constructing the shear and moment diagrams. I want you to see that it works, okay? All right, I'm going to give you a second on that and take another sip of my coffee. Did anybody have any post-traumatic flashbacks when I said the word MATLAB? That's what I said. I said, don't use, I can hear the groans. Yeah. Mathstand's a somewhat older but popular package, and it's very small, but it's pretty, like, it's powerful. It can do nonlinear, linear, buckling stuff. It's pretty cool stuff.
Do we use MATLAB in any other class?
In class, probably not. But let me say this, okay? Let me say this. That's a fair question. While you're copying this down, I'll answer that, and then we'll get back to this. When I taught 111, all right, I taught 111 years ago, and I think I might have mentioned this. I said, you might not use MATLAB, but what I do want you to take away from this is how an if statement works, how, like, the concepts of how loops work and stuff like that, because you might actually use those. You know you can do if statements in Excel, right? And if statements are pretty powerful for some real-world civil engineering calculations. For example, in steel design, the capacity of a column is dependent on your slenderness. And if your slenderness is in this range, you use this equation. And if it's in this range, you use this equation. You could set up a little if statement to do that for you. Boom. So is that useful? Yeah, it actually is. So even if you forget the MATLAB syntax, the concept, that matters. So that's my answer. Everybody good? Yes?
I just wanted to say, I think if you take finite elements, you also use MATLAB.
Oh, you might use it in there. If you ever take a course in finite elements, it is common that you do some programming, period. Whether it's MATLAB or Python or whatever, because, I mean, that's what MATLAB's all about. And so that you're curious, finite elements, that's how RISA and MassStan, these programs I'm talking about, that's how they work. So we might talk a little bit about that near the end, so that you kind of have an appreciation for what that is. All right, everybody good? All right. Now, one of the things I didn't write here, but I think should be pretty apparent, is that AX is 0. There are no horizontal loads on this structure, which, by the way, even if there were, we really wouldn't care, because horizontal loads on this beam would only serve to change the beam's axial forces. We're not drawing axial force diagrams. We're drawing shear diagrams. We're drawing moment diagrams. And the only forces we care about when we're drawing those are transverse forces, perpendicular to the line of action of the beam. Okay. All right. Now what I'm going to do is I'm going to sum moments at A to determine the reaction at C, and then sum verticals to determine the reaction at A, right? That shouldn't be all that magical, okay? So we got that. Now, I got this distributed load. I'd like to collapse that into a single point load. I have 3 kips per foot acting over a distance of how much? 60 feet. So what's 3 times 60? 180. And 180 is acting at a moment arm from A of what? Yes, 30. So now I got something I want to say about this operation I'm doing right here, where I'm collapsing this into a point load. That's very, very important here in a bit. Okay, so we have 180 times 30. We got 30 times 40. Don't forget that 60 kip load all by its lonesome. What's the moment arm for that 60 kip load? 80, there we go. Making sure everybody's awake this morning. All right, and then the only thing resisting it is CY at a moment arm of what, 60 feet? So let's see if we can do a little bit of math here. So 180 times 30, I think that's 5,400. 30 times 40, I think that's 1,200. And 60 times 80, I think that's 4,800. So 54 and 12 is 66, 66 and 48, that's 114. How'd I do? Did I do that right? All right. So 11,400 foot kips equals CY times 60. I might not be that good. What's that? 190. Hold on, let me scooch that. All right. If you noticed, I was lazy and I kind of copy and pasted a beam down here. I'm going to refer to that here in a bit. But for now, that doesn't really matter. Let me scooch this. All right. So now we're going to sum forces in the y direction. Put everything going up and equals everything going down. As for what's going up, we got AY going up. I don't know what AY is, but I know what CY is. That's 190 kips. And as for what's going down, I got 180, 30, and 60. So AY plus 190 is 180 and 30 is 210, 210 and 60 is 270. So AY is, what was that, 80? How'd I do? That, I went through that pretty quickly, but I think at this point, I mean, aren't we good with that? I would hope that by now that's not hard. All right, I'll give you a sec to catch up, and then we'll look at this shared moment diagram. Okay, everybody caught up? Okay, so since I'm lazy, I wanted to draw the shear diagram and the moment diagram sort of under this. So I repeated the beam. You don't need to do this on your calcs. I just did this here for the screen for the purposes of teaching. One of the things I'm going to do is I'm going to say, whoa, this is 190 kips, and this is 80 kips. I'm going to go ahead and write that in. But here's the thing. That's all I'm going to do, okay? In the original problem, in order to determine, so let's follow along with our calculations, right? So first thing we did was we determined support reactions. But in order to determine those support reactions, we took this distributed load and we collapsed it into a point load, right? The only reason that we did that was to make our lives easier when computing support reactions. The thing is, that is not what's really on the beam. What's really on the beam is a distributed load. So when you're drawing the shear diagram and drawing the moment diagram, you need to revert back to what's actually on the beam, okay? So I'll go ahead and tell you, if you use that point load, you will get the wrong answer, okay? This is what's actually on the beam. Okay. So let's draw our shear diagram first. So we'll do this. And what I'm doing is I'm just doing little guidelines under what I'll call like my points of interest. If you want this, you could do this like on a separate page. Like sometimes what I'll do is I'll do this on a separate page and I'll just say, like above this line, I'll write A, B, C, D. So I know I can refer back to the shear diagram. Well, you don't need to draw the beam again if you don't want. You can, but you don't have to. And then what I'll do is I will draw, again, that flat horizontal line. Let's see, where do I want to put that? We'll put that like right here. We'll call this V, kip. I'll put my little tick marks there so that I know that's the 0 line. And there we go. Okay, let me scooch that down just a little bit. There we go. Okay, I kind of like that. All right. So we do this the same way that we did it before. We start at 0, and hopefully we end at 0. So we start at 0. And what is the first thing that I do? Jump up 80, okay? Jump up 80. Okay. Now we got something new. Now we got this distributed load. Okay, so let's think about this. All right. First off, let's use our noggins about the behavior. The load between A and B is constant. So if the load is constant, what should the shear diagram look like? Linear. Okay, now let's talk about magnitudes. How much load exists between A and B? How much load between A and B? 120, right? Because it's 3 kips per foot over a distance of 40 feet, so that's 120. So if I'm at 80 and I drop down 120, what should I get to? Negative 40. So I propose then that the shear diagram in this region should look something about like this. And forgive me, you should have straight edges. So this is negative 40. And again, that's supposed to be a straight line. By the way, so that we're paying attention, what is the slope of that line? No math. You don't need to do any math. -3. The slope of the shear diagram is equal to the magnitude of the load. Okay. Now what do we do? Drop down 30. So if I'm at 40 and I drop down 30, what's that put me at? -70. That's exactly right. -70. Now, let's talk about this region right here. What shape should the shear diagram take? Between here and here? Linear. Positive or negative slope? Negative, because it's going down like that. So if I'm at 70, how much am I going to drop down in this region? 60, right? So if I'm at 70 and I go down 60, that puts me at what? -130. Okay? Now what do I do? I'm at -130. This tells me jump up 190. So if I'm at -130 and I jump up 190, what's that put me at? 60. So that's probably something about like that. Now what does the shear diagram look like from C to D? Flat, constant. And then what do I do right here? I drop down to 0. That, ladies and gentlemen, is your shear diagram. Not too shabby, right? That's simple. What do you think? Now, before we start getting to integrating and drawing our moment diagram, does anybody have any questions about what we've done so far? We're not done, so. Okay. So, in order to draw the moment diagram, we need to integrate the shear diagram. Okay? So what I propose is that we number these 1, 2, 3, 4. Okay? So let me show you what I've done. Okay? So 1 is this triangle. 2 is this triangle. 3, now what I'm doing for 3 is I'm saying all of this is 3. This whole kit and caboodle between B and C. Okay? And then shape 4 is this rectangle over here. Let's see if we can do a little bit of integration on this. Okay? Now we got ourselves a little bit of a problem. We got to figure out what's going on with 1 and 2. In other words, if I want to determine the areas of those triangles, I need this distance here, x1, and I need this distance here. But didn't we already talk about this? We just did this. That was the whole point of doing it earlier. What's an easy way of determining x1? Based on the numbers I've got here. How would you determine x1? All right, and so what is that? Give me some numbers. 80 divided by 3, right? 80 is the change in y, and that's the slope. So what is 80 divided by 3? Somebody help me out with that. X1 is 26.67 feet. And I propose then that X2 is what? How are we going to do X2? 40 minus, right? We could do 40 minus, or we could take 40 over 3. And 40 over 3 is 13.333 repeating, right? And does that work? What happens if you get x1 and x2 and decide to add them together? You get 40, right? The big 40. Okay. With me so far? All right. So let's see if we can do some area computations off to the side. So somebody help me out. What is, I'll do this like right here. What is the area of 1 going to be? I'll do this one. So it's 1/2 26.67 times 80. And what is that? 0.667, go on repeating, right? Right? All right. Now what about area 2? Somebody else set that up for me.
1/2 13.33 times -1.
All right. Now what does this give us? It's a negative.
-266.6.
Something like that. Negative 266.67. All right. Now, does anybody remember how to get the area of a trapezoid? Does anybody remember how to do that? Everybody? Okay, I want to talk about this. So there's a couple ways of doing this, right? Now what he just said is you could split this up and you could get the area of the rectangle and the area of the triangle. Like you could do that, okay? Now I'm going to give you an easier way to do it, okay? An easier way to do it is this. All right? First off, both of those shapes have a width of what? What's the width? 20 feet? Okay? I propose that the easiest way to get the area of the whole thing is to average this and this. And if you don't believe me, here's what we're doing. Right? Here's what we're doing. We're basically trying to figure out what this point is and take this little triangle right here and put it right there. And so this distance right here is just the average of that, and that is 20. Does that make sense? I'm just being lazy. I don't want to do 2 sets of calculations. What do you get when you do this? It's negative. Say it again. 1,000? 2,000. And here's the thing. If you don't believe me on the math, I'm going to show you something. What's the area of shape 4? It's 60 times 20. 1,200. What is that plus that plus that plus that? 0. So obviously I did something right here, right? All right, what do you think? So far so good? Okay, all right. If it's okay, I'm going to take these areas and sort of move them out of the way. I'm not going to get rid of them, I'm just going to move them. I'm not getting rid of them, I'm just moving them out of the way. Okay. Now what I'm going to do is this, okay? I'm going to continue my guidelines down, but let me show you something. See this point right here? See this point where the shear diagram crosses 0? Okay, I'm going to make another little guideline that goes down like that because that's kind of an important point. All right. Let's see. Okay. Now we're ready to draw our moment diagram. Now before we start drawing any lines, I just want to get my values right, okay? So watch me and bear with me, okay? So we're starting at 0. What happens from here to here? What's the area from here to here? I know that's what the shape looks like. I'm talking about the areas. What do we get for A1? Okay, so would you agree that from here to here, I have to go up 1066.67? So that's where I'm going to be. I'm going to be like, I don't know, right here, 1066.67. Would you agree with that? All right, now what happens from here to here? I go down, how much? 266.67. So if I'm at this and I go down 266.67, what's that put me at? 800. Does everybody see what I'm doing? Now what's the area of shape 3? Negative 2,000. So if I'm at 800 and I go down 2,000, what's that put me at? Negative 1,200. So that's going to put me about, like right here. And if I'm at 1,200 and I go up 1,200, that puts me at 0. So is everybody okay with sort of what I did here first? I'm just like figuring out what the values should be. Now, okay, I want everybody to watch this next part. So I know that there's some people that are still copying some stuff down. I'm going to give you a minute because I think this is important. All right. Everybody good? Okay, so watch this. Now, this first region from here to here, okay, this first region, this is a linear shear diagram, right? Linear shear diagram means it's got to be a parabola, right? A quadratic moment diagram, okay? I propose that there are 2 ways that parabola could go. It could go option 1 like this, or option 2, it could go like that. This is option 1, option 2. Which way is it going to do? 1, right? A lot of shear to a little shear. A lot of slope to a little slope. What's the slope of the parabola got to be right here? 0. Why? Because the shear is right there. So whenever the shear is 0, let's go back to Calc 1 land. Whenever the shear is 0, the moment better be a relative maximum or minimum, right? Going back to all that stuff you learned in Math 229. So I propose that the parabola looks something about like this. All right. I'm going to move that. Oh, I didn't mean to do that. All right. Yes?
Okay, this might be a dumb question.
No, it's fine.
But I could never wrap my head around the little slope law, so very static. So if it opens down because it's negative slope, and if you had a parabola, it would be like this. Is that always the case?
Okay, what?
So like a negative parabola goes like this.
Yes.
Like this, and since it's a negative linear line, is that the correlation?
No. What I'm saying, this is what I'm saying. Okay? You're thinking like first derivative, okay? Maybe the best way of thinking about it would be second derivative, but just look at it like this, okay? That line is bigger than that line, right? So the idea is that that slope is bigger than that slope. So how do you draw the parabola such that the slopes match the values of the shear diagram? And the only way is for it to do that. Does that make sense? So likewise, when we look at this region, the slopes increase and the shears are negative. So the slope has to go like this. It has to increase in magnitude and it has to get negative. right? Because these are negative slope. This is a negative slope, right? Remember, if you draw a line like a negative slope goes like that, this is a positive slope. So think, as the shears get bigger and get more negative, the slope has to get more negative. Does that make sense? Did that answer your question?
Maybe.
Kind of. We're going to have more examples that I think will illustrate what you're talking about a little bit better, because we haven't looked at the other side of it. Don't worry. Don't worry. Oh, sorry. All right. Okay. Let me ask you this. Okay. See how the shears increase from here to here? Right? It's a parabola, but as the shears increase from here to here, the slope has to increase. It has to get steeper and steeper from here to here. And the slope has to get more and more negative. So mathematically, what happens from here to here is that you have a sudden increase in how much your slope is changing. So it's going to be another parabola, but it's going to go down like that. Does that make sense?
So I know it's kind of hard to show it on like when you're actually drawing it, but since you've got that 30 pip drop, would it change right at the point?
Yes. Yes. What it should look like is it should look like this. It should go like that, and then like that. Oh God, that's horrible. You get what I'm saying? See,
It's just hard to show it.
it's hard to show it. So maybe a better way is it goes like that, maybe like that, and then like that. I can't do it better than that. That's why I use Excel, because Excel can do it a lot better than I can. Now, just so we're paying attention, what does the moment diagram look like from here to here? Straight line. Here might be a way of looking at it mathematically. So the shear diagram is a line with a negative slope. If you take the derivative of that, you'd get -3, right? So the second derivative test would tell me that this is a parabola that's concave downward.
So that's what I was saying.
Yeah, that's one way of looking at it.
Basically, if the line was going like this, like all the
Yeah.
diagrams were going like this, it's going to be up.
Yeah, if the shear diagram was going like that,
But if it's down, the correlation is the parabola is like this. Negative slope. Down slope.
yeah, for the most part. I don't want to say always is and nevers, because you could have some beams that are loaded upwards. So, yeah. All I can say is that with more examples, this picture is going to become clear, because there's a couple other things we haven't talked about: concentrated moments, what happens with triangular loads, etc. So just give me some time. So, all right. Does this make sense so far, though? Is it so far? Okay. All right. I'm going to take this and make it more complicated, and hopefully that'll make it make more sense. All right. Laptops on during next lecture. Don't forget.
Look, that'll be the one day I don't bring it.